This is section 5 of the module 7 lecture, and we're going to start reviewing the concepts in chapter 8 with this recording. And so we're going to look at the estimation of population parameters, which is what is covered in section 8.1 of the textbook. All right, up to this point, we have calculated probabilities using discrete probability distributions in chapter 5, then the normal distribution in chapter 6 and 7. Of course, in 7, we're using the sampling distribution, but still was a normal distribution. But if you recall, in every case, we were given the parameters of those probability distributions. In chapter 5, when we calculated binomial probabilities, we were given the probability of success. When we use the Poisson distribution to calculate the probability of a certain number of occurrences in an interval, we were given the average of occurrences in an interval, lambda. And whenever we use the normal distribution in chapter 6 and 7, the population mean mu and the standard deviation sigma were always given to us. Now, in general, those parameters are not known, and they need to be estimated with data from representative samples taken from the target population. Because in order for us to know these parameters, we will have to evaluate every element of the population. And as we saw in chapter 1, well, that sometimes is too time-consuming, too expensive, or just impossible. So we're going to rely on a sample, and the data from a sample and the statistics we calculate from that data to estimate these parameters that in practice they are not known. So if you remember the idea of statistical inference that we reviewed in chapter 1, so in chapters 5, 6, and 7, we were given the parameters as if we knew all the characteristics of the probability distribution of the population. In general, we don't know that. And because we cannot study the entire population, we take a sample, and hopefully a random sample, so that from the data in this sample, then we can calculate the different statistics. Like here I'm showing the sample mean and the sample standard deviation. And you have the histogram of that data that sometimes that is used to estimate what is the shape of the probability distribution of the population. Now in here, we know if this is a random sample and there's no non-sampling errors, so the mean that we have from the sample is not going to be exactly the population mean because of the sampling error. But nevertheless, we're going to learn to make inferences with these statistics. All right, let me review the estimation procedure. We talked about this in chapter 1, if I'm not mistaken. So first, the objectives of this estimation procedure is, one, identify the population of interest that we call the target population, identify the variable of interest, the thing that you're going to measure on those elements that you took from the population, and then you determine what population parameter is of interest. Once you do that, then you design a data collection plan where you randomly select a certain number of elements from the target population, and then you measure the characteristic of interest on each of those elements that you selected. Once you have that data, then you graph the data and calculate sample statistics, as we learned in chapter 2 and 3. And then you start calculating different estimates of the parameters, like the interval estimates, or you test hypotheses, as we're going to learn in chapter 9, or you fit a model, like a regression model that we're going to learn in module 13, or rather in chapter 13. And then you verify the assumptions behind this thing, so that's part of the analysis. Once you have completed your analysis, you need to interpret the results of the analysis. Because based on this interpretation of your results, you will make recommendations and suggest decisions to be made. And that's why I've been insisting so much on interpreting the results. This is good practice when you are learning statistics and performing a statistical analysis. So from now on, we're going to assume that the population of interest has been defined, the variable of interest is defined, and the problem we're given, it tells us what parameter they want us to estimate, and they tell us what the variable of interest is, and they will give us some data that hopefully was collected properly, but they give us either the data or the summary statistics from that data. So with that information, this is where we're going to focus the remaining part of the course and the analysis. Not so much the graphical analysis, but rather using these estimation methods. All right, let's start with some definitions. The first definition is that of an estimator. This is a sample statistic that estimates a population parameter. An estimate is the value or values assigned to a population parameter, and a point estimate is the value of the statistic calculated from a sample. In this table, I'm showing the different parameters that we encounter in chapters 5, 6, and 7 when we calculated probabilities. So now we know that the sample mean x bar is the estimator of the population mean. And we know that the sample variance S squared is the estimator of the population variance sigma squared. And we know that the sample standard deviation S is the estimator of the population standard deviation. Also, we know that the sample proportion is the estimator of the probability of success of pi. And also we know that the sample mean of the occurrences in an interval is the estimator of the population parameter of the occurrences in an interval lambda. So here are the estimators and here are the parameters. So keep that in mind. All right. Here's an example to see what a point estimate is. So in this example, we took a sample of 10 children that are in 4th grade, and we weight them. The weights of these 10 children are here on this table. And we would like to estimate the mean weight of all 4th grade children. All, that means the population mean. So the parameter of interest is the population mean mu. And we saw from the previous table that the sample mean x bar is the estimator of the population mean. Now in chapter 3, we learn to calculate the sample mean, and that's what I'm doing right here. So if you sum these 10 values and divide it by 10, the value of the mean is 20.1. And if you notice, I'm using this OBS that stands for observed. So this is the average observed because it comes from the observed data in the sample. So I want to make that distinction to see that this is the point estimate. So in this case, then the point estimate of mu is 20.1 kilograms. So point estimate is just the value of the statistic calculated from the data. All right. Oh, and one more thing. If you say, well, how close is this 20.1 kilograms to the actual value of the mean? Well, we know from the sampling error that this thing may not match exactly the value of the true population mean, but we know it's close. For that reason, we'd like to introduce another method, or another estimate rather, called the interval estimate. This is an interval constructed around the point estimate of the population parameter, and that we believe contains that population parameter with a certain level of confidence. And that's defined as a point estimate plus or minus this quantity called the margin of error. And the margin of error, we use a capital letter E to designate the margin of error. And this estimates how far the point estimate is from the actual population parameter, and is defined as K times the standard deviation of the sampling distribution, where this constant K depends on the level of significance. So what is this level of significance? Well, this level of significance we designate as 1 minus alpha times 100%. Alpha is the Greek letter alpha. And this level of confidence is the level of confidence that, is the level of confidence that the interval estimate contains the population parameter. And then this alpha value is called the significance level, and that's a probability. And it's a probability level at which it is decided that a point estimate is too far from a population parameter. This definition will become clear once we discuss chapter 9. But I wanted to point out this. The most common levels of confidence are 90%, 95%, and 99%. So if you notice, 1 minus 0.1 times 100% is 90%. And 1 minus 0.05 is 0.95 times 100 is 95%. And 1 minus 0.01 is 0.99 times 100% is 99. So from that you can see that for a 90% confidence level, the alpha value is 0.1. For a 95% confidence level, the alpha value is 0.05. For a confidence level of 99%, the alpha value is 0.01. This is going to be helpful in determining this constant right here, as we will see in subsequent slides. All right, so let me stop here. In the next segment, we'll discuss the confidence interval.